Okay, so thank you for coming. My name is Mario Fusco. I work for Red Hat. I'm the project lead of Druls, and from time to time I collaborate also to Quarkus development.
I'm Francesco. Many people call me Franz, not my wife, actually. And I work as a performance lead for Quarkus, and I work in Red Hat in the performance team.
Okay. And the reason why we are here today is that we would like to talk about performances and profiling. And yeah, one of the reasons why we started doing this thing at large is actually because last year I gave a talk about virtual threads, about Project Loom. And at some point, I started showing some flame graph. I don't know if any of you was at my talk last year. Yes, somebody. And at some point, I started showing some flame graph, giving them for granted. I mean, and I wrongly assumed that everybody can read a flame graph, and I was surprised that this is not the case. And we want to pass me the term. We want to fix this thing. We want to educate the average Java developer, whatever he or she is, to care about performance and have a clue on how to measure them and how to possibly improve them. Okay, but what is really profiling? Yeah, speaking about performances, because this is the very first thing that comes to us in mind when we speak about profiling. Okay, we do profiling to improve performances, to make our code run faster. But this is actually just one part of the story. What is performance in reality? Performance is we want to consume less CPU cycles to do a given task, okay? So what we are doing, we are using a resource that in that case is the CPU, and we want to use it in the best possible way, okay? But the CPU is only an example. The cache could be another example. The memory could be another example. And we may want to optimize the throughput, or we may want to optimize the latency. So in reality, what profiling is at large is not only let's make my code faster, but let's make consume the resource that I have at disposition in the best possible way, okay? So maybe also consume less, be more eco-friendly, or stuff like this, okay? And there are a few different type of profilers, and we will focus on a specific one. But generally, when you do profiling, you either do profiling on an event-based way, meaning that your code explicitly or implicitly emits some sort of event. I'm allocating an object, for instance, and you gather this event and put them together and make statistics out of them. And then you have statistical profiling, profiler that are the profiler that take samples of what's happening in your code. I mean, for instance, they take samples of the points when your CPU is using cycles, or when you are creating memory again, or you have a cache missing again, and you take statistic out of them. And then you have instrumentation which we try to avoid using because it is the most invasive thing, okay? If you do instrumentation, meaning that you are instrumenting the code that you want to profile, and then in some way you're also altering, you are modifying that code that probably in a way that can impact the measurement itself. So probably instrumentation is the very last option that you may want to consider. Okay, so I'm speaking about profiling, and the point is, okay, but why you don't do it, okay? Because my premise was, okay, I gave for granted people do profiling or use a flame graph, and to my surprise, I discovered that most of you don't. And we started wondering, okay, why you don't do it? Okay, and probably you are lazy, you don't want to do it. I don't think this is the case. Otherwise, you won't be there. Maybe you don't want to know. It's better to hide the problem under the sand and forget about it. I hope this is not the case as well. This is quite a common thing, okay? Especially for Java developer, because in Java you have tons of level of abstraction. You use you run into a container, and then you use a framework, and then the framework runs on the JVM, and what the hell is going on there? It's not my business. I'm just a Java developer. I just write my code. I don't care what the Java virtual machine does. I don't care what the garbage collector does. I don't care about what the JIT compiler does. And my point is that you should do. You should care about this stuff. Okay? And this is another very common thing. Unfortunately, I saw this also with some friends and colleagues from time to time. Yeah, I don't need to measure this because I know what's going on here. Okay? And the reality is that no, you don't. No, you don't, exactly for the reason that I was saying before. There are so many layers in the middle, the container, the framework, the Java virtual machine, and the hardware, the different cache lines and whatever. And there are so many things in the middle that nobody can imagine really what's going on. Trust me, you don't know. You cannot know, okay? So you cannot know. The only way to know is to measure it. You cannot guess. There's no way around to try and measure what's going on really. And often you are surprised. I mean, this happened quite often to me. I assume, okay, yeah, I know the problem is there. And no, the problem is not there. When I measure it, it's somewhere else. And even worse, I assume the problem is there. I work hard for 1 week to fix the problem there because I'm convinced it's there. And nothing happens, nothing improves because the bottlenecks was in a totally different place, and I wasted 1 week of work. And you don't want to do this, right? Okay, so yes, and at the end of the day, I, especially with the help of Francesco, so that's why I say we have lots of fun doing this thing, right?
Masochism.
Yes, well, Francesco made me appreciate the funny part of this job. Okay, and in reality, this is a sentence that is very often mentioned, and I did myself quite often in my sometimes opinionated tweets, or they are not called tweets anymore. I don't know how to call them, but yes, this is something that people say. Okay, at this moment, I don't care about optimization because it's the root of all evil. If I do premature optimization, I'm making my code harder to be read. I'm hiding some detail and emphasize some other, and I don't want to do this, so I don't do premature optimization, okay? And with this, I could conclude my talk, ask if you have questions, I'm done. We don't do it, and that's all, okay? But this is, in reality, only part of the story. This is only part of the complete quote of Donald Knuth, okay? He said, okay, premature optimization, yes, is the root of all evil, but you don't want, the fact is that you don't want to do it on the complete of your code, of 100% of the line of your code, right? The fact is that there are generally the 3% of the right of the lines of your code that are on the critical path, okay? And if you want to do profiling, your first goal is to identify those 3%, otherwise you will end up doing what I said before. You fix something that you are convinced that that was the problem, and the problem is not there. So the first thing is to identify that 3% that is on your critical path, and then you figure out what you want to do there, okay? And if you don't do this, you are not an engineer, sorry, okay? We engineer works with data, and an engineer without data is just another person with his own opinion, and that's all. And yeah, I don't like to go there, okay? So I hope I convinced you that, or tried to convince you that we want to do some profiling, we want to understand more what's going on, and to do this, we need some tool, okay? And so the remaining part of this 3-hour-long chat conversation is to learn some of this tool, learn how to use it, and learn how to interpret what they are telling us, okay? So first of all, let's start with a very simple code. We have a method of function A that calls a function B calls function C at D, and does some work on its own. And then function C does more or less the same amount of work of B, and D does more or less the double of the work that B and C do, okay? So this is my situation, okay? If I try to measure this thing, and I'm showing you this because I want to map this thing into a flame graph, right? So if I try to generate a flame graph out of this thing, this is what I expect, okay? So I'm trying to explain how to read this thing, okay? So what do you see here? You see that at the bottom of the stack, you see the thread running, of course. At some point, you will start seeing your code. You see the method A, okay, that takes the 100% of the computation here. Here, in this case, you can profile different events with Async Profiler, which is the tool that we are using during this session. I'm sampling here the CPU. Okay, so what is going on here is that A is calling B, and okay, A doesn't do anything on its own, so A take 100% of time or samples, and B is doing the same. And then, as you can see, B do some work, and then C do more or less the same amount of work, as I said. And then D, the portion of D is the double of the portion of C, because we said that it does the double of work. And this is as simple as this. This is how we read this flame graph. There is no meaning in the order of the x-axis. It's just alphabetical order. So and of course on the y-axis you see the stacks. Okay, and that's all. So the only thing that you need to know is that the size of a line is proportional to how many samples Async Profiler took while the CPU was in that particular method. Okay, and this is only part of the story. The other part of the story is that these things comes with some fancy colors that, of course, has a meaning. Okay, so, and it's also important to understand what are the meaning of all these colors. So the green that you see this here is for normal Java code. You are invoking a Java method. And then the blue, the light blue, the aqua code is for inlined Java. It's when the method is inlined. And if you don't know what this means, I have a slides for this later. And then you have in orange, you have the kernel code, because yes, the Java virtual machine, this is something that you really see with this tool and which is nice. The Java virtual machine is per se a software that does other stuff. On top of running your program, it does other stuff, okay? And you want to understand how everything's come together and figure out, okay, maybe the garbage collector is doing too much work and I don't expect this. It's maybe because I'm allocating too much and I don't expect it and I need to investigate why. Or maybe C2 is doing some more work than I expected because he's trying to optimize and they're optimizing continuously the same part of code for some reason and I need to know why. So you have the kernel code here that is typically, for instance, when you do a context switch on a native thread, that's a part of kernel code that is running. You have in red the C library, so typically when you do a JNI call. And then in yellow, you have the C++ stuff that is typically internal of the Java virtual machine. So typically in yellow, you see mostly two things: the work done by the garbage collector, and if your code is not hot enough, if you didn't give it enough time to warm it up, you see C2 doing its cheating job, its optimization, okay? And I spoke about inlining, okay? How many of you know what inlining is? Okay, quite a few, nice. Inlining is probably the most important optimization, and this is why in Flame Graph it has a dedicated color, okay? The problem that you want to solve is that calling a method, it's a costly operation, okay? Because you need to put one more thing on the stack, and you need to deal with how to pass variable, and you want to do the opposite when the called method is returned and you collect the result, okay? And you may want to avoid this thing. So one of the main optimization that the cheat compiler does is inlining this stuff. So if you have this a method on the top and another function that is using the method of the top, what actually happens inside in the code that you are running is that you are not, the second function is not continuously calling the method down the top, but what the JIT compiler does is, let's say, copy the body of the inlined method into the caller, okay? And in this way, you can save a method invocation. So when you typically see that aqua stuff there, they are only inlined code, meaning that it's not really actually that method, but it is inlined in the caller. And as you can see, this can happen at many different levels. This is configurable. I believe there is a limit, which is like 15 now, right, Francesco? It's like 15 calls, but this is configurable in the Java virtual machine, even though I don't suggest you to touch it. I mean, it's 15. I know it's a magic number, but it's there for a reason. And yes, okay, so one of the first things that you check when you look at a flame graph is say, okay, how much aqua color I see? Because if it's not enough, you have a problem. The JIT compiler is not doing this optimization for some reason, and you need to understand why. And then, yes, as I said, there is lots of other code which is not properly Java code, but you want to profile as well. Okay, so you have kernel code that is used for page faults or for cache misses. It's used for the native thread switch. You have the C++ code that, as I said, is mostly the JIT compiler and the GC. And you have intrinsic, and you have native code that you may want to call through JNI. So there are lots of more stuff than not only the Java code on which you should care. Okay, and
okay, so before starting, it's the year of artificial intelligence, so I'm really surprised that the subtitle generator with 2 Italian on the stage is kind of working. That's incredible.
I wasn't reading it, okay.
Yeah, we are able to break it every
working,
time,
okay.
actually, so that's any kind of work for real. And then my wife, because it's her birthday today. So let's move to the challenges of profiling. Actually, is not just profiling. It's profiling on the JVM. So it's something very specific. How many people has ever heard the save point term? They have, you have a very bad day today, probably. So, but this is the description in the hotspot glossary. To be honest, I won't invite anyone to fully read it, so I will give you a unprecise but still decent enough summary of it. So, save points are supposed to be point in time in which cooperatively, kind of, the Java code is supposedly to not mess up enough and let the just-in-time to perform very specific optimization. Not just optimization, operation in general. And there are quite a few of these operations that expect the Java code to not doing anything like mutating the heap or things like that. Why is that important? I will go through this. So there are few operations required by the JVM that require to reach the local or global save points. The ones interesting to us are get all stack traces and get stack trace. Why they are important? Because actually, as we said before, a profiler is supposed to be able to collect sample of stacks, right? So how we can collect it? By using specific method provided by the JVM, in theory. The point is how is actually doing it. So the just-in-time compile your code in theory in an assembly form, or it could be interpreted whatever. And it's making traps called save point polls, by which, depending if an actual save point request has been issued, it could block the current thread that is going to execute the poll. This mechanism means that from a statistical point of view, you can observe the stack only in the places in which the JVM decide to block. If you think about it, it's weird. I mean, if it can decide, but it doesn't decide well, it means that whatever stack trace is being collected is biased, no? It's biased and maybe it's not collecting the information we care for real. Because if we have a page fault or something outside of the Java world that happen and there is no save point poll there, you won't know what's going on. Okay? Quindi, so the save point biasing is one of the problems with the JVM profiling. And additionally, you have an observer effect. So in this case, for example, I attached JVisualVM. How many people knows about it? I would say a lot of bad things on this tool, but still for profiling. Because it's making use of this API to collect stack traces, because are definitely the official way to collect stack traces. And when you do it, this is the output of the save point logging that tells for how much and how many times your Java thread stopped. Because when you perform this operation, you are at the save point, so collecting the stack trace. So the longer you take it to do it, the longer the whole Java things will be resumed. So you are observing a system and disturbing it, changing its performance characteristics. So it's not a nice effect. And so these are the two main, let's say, important challenges about the Java JVM profiling, sampling profiling. So I take this slide from Johannes. I have no idea if he's around. Maybe it will be the next days, actually. He worked for SAP on a new way to collect stack frame for the JVM. And not only, he's working hard to improve the existing methods. This is a taxonomy of the type of profilers that exist. It's not a complete list of the profilers, but the type of profilers. So you can have external profilers, so the one that make use of some API exposed by the JVM, and among the external one, you can spot Visual VM. NetBeans, I have no idea they have a profiler, so my fault, but exist, it seems that exist. And they're making use of this synchronous API. Why synchronous? Because of the save point machinery that I told you about. And async. Async, what it is this Forte? How many people? Oh, okay, you are not a young one. Because Forte is pretty, an old thing. So there is an API and an official API called Async Get Call Trace. This API is exported in a way that, in theory, you can make use of it, and is capable to collect stack traces having two important characteristics. One, it can make everything to crash. That's not a good one. The second one is not working at a save point. So it's not save point biased. But it opens the door to a whole can of worms, because it means that maybe the stack is not even complete. Maybe it's not exactly where you expect it to be. Maybe the method ID assessed make it crash when you try to reach it, because you have concurrent class loading and unloading now. So there are many things. One of the profiler that exploit this specific API is Async profiler, so the one that today we are going to talk about. To be honest, Andrei Panjin, that is the author of Async profiler, created an alternative way that is making use directly of the internal data structure of the JVM in order to collect stack trace without relying on Async Get Call Trace. But the benefits are the same, let's say. So it's capable to observe the word without waiting for save points. On the other side, you have the built-in type of profilers. Java Mission Control, JFR, way more. So JFR is actually making use of an engine that under the hood is relying on similar-ish mechanism of Async Get Call Trace, so it doesn't suffer from save point biasing, but still we will see that as a Swiss knife, or today developing, observing of profiling and performance of your system, probably Async profiler is more handy, but it's personal, really. So Async profiler is an hybrid. Why is an hybrid? Hybrid between what and what? So we talk about Async Get Call Trace. Definitely is a thing within the JDK. It exists, allows to collect these stack traces in a synchronous way. And then you have a perf event. How many people knows about perf event? So there is an API in Linux that allows you to collect information about specific resources you care about and events. Could be the CPU usage and produce call stack and backstack of the native side. Async profiler is marrying the two things. So you are able to see the Java side of the things, and then you are able to see the rest. And that's how it's capable to collect stack traces that contain both the information, because the JVM doesn't know anything about the rest of the stack that belong to the operating system. So you need something external that tells you. And this one, the perf thing, is that one. Have a very low observer effect, this profiler, and is capable to profile a lot of things, not just CPU cycle profiling. And it's open source, so I can really ping a lot this poor guy and Andrei Panjin. So no, it's is awesome, but and he's very open to speak, and you can open an issue, you can talk about it. So it's an open source tool with all the good things out of it. About the perf stuff, we are not going to go that deep, but if we do it, tell me if you want to leave so we can close the door, because we still will go through it. Not that much, really, just tiny bit. So perf under the hood, what it is, actually, I mean, it's not rocket science. What it's doing is the async profiler asks to memory map, so a ring buffer, so a queue, basically. It tells, okay, I would like to know about this specific event, and at a specific moment, depending by the type of event is interested in, this event will be collected by the profiler. So it's just an interface to talk with the Linux system. And the type of, not the type of event, but the type of information it brings for each of the sample is the stack trace. Very simple. So you can search on perf man and you will find it. You should be aware of a couple of additional challenges, let's say. These challenges are not related, is not a limitation of the JDK this time. And, you know, probably many people when come to this workshop were expecting to see, okay, now I know. No, you know that you don't know. That's the point. So we should be aware of the complexities and the problem that exist. And these are not really solved. The skidding is one of them. So that's why I was talking about perf. So considering how perf work for software event like the CPU cycle, so it's the virtual time by which a specific thread is executing on CPU. So the consumption on CPU side that the kernel is aware about. When the actual consumption reach the specific threshold that the kernel decided to be the one that will emit the creation of the event sample, it's going to create a signal for that. So in short, there is an asynchronous process by which, okay, this is going to happen now, but the actual now is being consumed later on. And when you observe the word in the later on part, the word maybe has changed. But what word? Your stack trace. Maybe you are in a different part of your code. And it's going to be blamed as the one to be consuming CPU. This can happen because CPU are pipelined. You can search on Wikipedia. But the idea is that you should never blindly trust data. We collect data, but we don't trust it that much. Enough. So there are other challenges. The inherent challenges that the people usually compare Java Mission Control and JFR with a async profiler and say, yeah, but you know, one is better than the other. You should be aware first what they measure, because what they measure is different, actually. Or you can make a async profiler to measure the same thing. But one of these things is you, by default, with a async profiler, you have a CPU on CPU consumption. That means that the Linux stack tells you how much you are on CPU, it produces a sample stack, blah, blah, blah. Wall clock profiling is a whole different beast. Because let's say that you have, it's pretty usual that people love to have a thread pool with 1 million threads. You know, it's pretty handy. And all these threads are not doing anything. Okay? And you have an engine that is supposed to collect how much the time resource is spent, not the CPU. It's a different resource. As Mario has said at the beginning, they are measuring different things, wall clock profiling and on CPU profiling. The wall clock profiling, even if threads are not doing anything, is supposed to check that they are not doing anything. Okay? So the amount of work, of sampling work of a wall clock profiler could be way more. And usually they subsample. So they tell, okay, we have 1 million of threads. We should decide for each one of each 10 milliseconds how many I'm going to check what's the state. because it can't do it for everything. And that means that when you run a wall clock profile, you should be aware that you are looking at a portion of reality because of a limitation of the tools, but it is what it is. But you should be aware of it. And now the pitch part. No, it's not a pitch, actually. So as I told you, I'm the Quarkus performance lead. So in this case, one of the interesting part of profiling is not to profile a micro benchmark. Because in the real world, you have tons of things in the stack. So we would like to show why is handy or is not that handy to have a specific visualization format. So in this case, we are going to use a Quarkus application. That is a kind of Chinese box. And it's not a pitch, actually. You should be aware of the internal. So observation, in order to be interpreted correctly, requires some knowledge. And in this case, I'm going to tell you that Quarkus itself, for the more external part, is the type of package, the things you would look at. Then, going deeper inside, you have the REST-easy reactive things that handle all the REST part and HTTP, whatever. Under the hood, we use Vertex, so we can search for the Vertex package in our flame graph and look what's going on. And really, really under the hood, we have Netty. Netty is an asynchronous networking I/O framework. And it's the one that talks with the kernel most of the time. So exchanging bytes with your network interface. And now we need to know another thing. That could be probably the same in whatever kind of application you would like to profile. You need to have a general idea of the dynamic of the system, how it works. So in this case, for example, Quarkus have, as we said, the I/O threads that are the one running within Netty. These I/O threads are fixed, are a pool that never changes, always the same. They are the ones that are capable to consume user event in the form of runnable or scheduled task, or actually read out of the network and write to the network. And later on, the part you have control on when you write your application, you can decide to run the user level code in the same I/O thread, in the find handler and dispatch to event handler, whatever it is, the first block. And then the second one, you can instruct Quarkus to spawn and consume the actual request outside in a blocking thread pool. So there is a jump in another thread pool. Recently, we added the for join inner pool of virtual thread. So you can have these other option. But the point is that you can perform two type of dispatch. No dispatch and dispatch to an external event executor. And now let's have some fun. Okay, so close the door. No.
Yeah. This was just an introduction to give you, again, a bit more of context. And again, the idea is to profile some REST endpoint, okay, made with Quarkus, but this is not the main point. The main point is that we wanted to give you a real-world context, not an ad hoc micro benchmark, because very likely it's the thing that you will end up doing in your day-by-day job, okay? So we created, okay, there is this one last slide. We created this project when we will do our experiment today. I invite you, if you want to clone it and try it at home, because there are a few tools in it, and it's nice to check how it works. We created a script command that you can reuse to in a very convenient way. So probably you can reuse, or I hope you can reuse part of it. So what we are doing is that we have this web application, okay, with a few REST endpoints. And what we will do during the remaining part of this deep dive is using Hyperfoil as a load generator. So Hyperfoil will call this REST endpoint in a continuous way. And we will generate some flame graph out of this execution and see what happens and try to interpret them. Okay. So what I have here is this script. Okay. And this is the main reason why I invite you to clone this project, because we created this script that actually allows you to create a load with a perfoil and then to automatically collect the statistics using Async profiler. So it's quite convenient, okay? So what, yes?
There are just a couple of parts of the script that
you want to underline. Okay.
Yes, nothing fancy, but is necessary to make things to work. Is related to what we have said before. So in the line with the actual Quarkus start, there is an unlock diagnostic VM option there that if you keep on reading, should add debug information on non-safe point operation or something like that. I don't remember by heart. Debug non-safe points. It's related inlining. So inlining are operations that can save some safe point poll to be removed by the just-in-time. And if you don't have debug information when you are in an inline method and the profiler goes there and would like to know what's going on, which method you are within, is not capable to know that because that method actually doesn't exist. As Mario said, it disappears, the call itself. So in order to have boundaries of which part is the one to be blamed with the right method name, you need to add this. This is going to increase slightly the footprint probably of your application because of the debug symbol, but at the same time is necessary or you won't be able to spot the actual method to blame. So it's very important. The other thing is related to the number of IO threads. So you can see the threads part here. And by default, when we start Quarkus, we decided to use 2 IO threads that are the event loops of Netty that are capable to exchange data from the network. Okay? I don't have anything more.
So let's try to put this at work. And this is the first REST endpoint that we want to try. And it's, you know, quite surprising that we can learn something from this thing, right? Really, should we really investigate this stuff? Let's give it a try. Okay, it's pretty clear what it does. Okay, right, I don't need to explain, I guess. Okay. So I have this, I'm running this benchmark script. Okay, normally you need to specify the URL that you want to ping, that you want hyperfoil to generate the load. But yeah, by default, it is pinging that this hello endpoint, so I'm not adding any URL for now. Okay, so I'm running this script. Okay, the very first time that I started, it asks my root password. This is because it needs to send 2 calls to the kernel to enable some flags of the kernel that allows Async profiler to gather the statistics. Yes. Okay. So, okay. Let this running and let's try after to read what is going on here. Okay. Okay. So now it's running. Okay. So it's done. So let's start reading what's going on. Okay. So what we are doing here is that this benchmarks runs for 40 seconds, The first 20 seconds are for the warm-up, so I'm not collecting statistics for those 20 seconds. And the other thing is that we configured Quarkus to work with 2 worker threads. We have 2 threads and 10 parallel collection, pinging those threads, pinging the REST endpoint to ask Quarkus to provide the result. Okay, so what happens at the end of this execution? It generates this HTML, which is actually the flame graph. Okay, so let's start giving a look at it. Okay, let's maybe do this. Okay, so probably I can make it bigger. Okay, so let's try. Can you read it? Okay. So what's going on here? First of all, I said, okay, I want, you want to,
Yeah,
well,
yeah,
I don't know if, it's better probably to point here. First of all, I configured Quarkus to run with 2 worker threads. Okay, so I expect these 2 threads to do their job. And what is surprising to me at the very first look is that I do not understand why I see all these other threads, right? Okay, so I expect these 2 threads to do the job, but this is not really what's happening, and this is the first surprise, okay? The other thing is that to interpret what's going on really, we need to do 2 more things. We need to count the number of samples that each thread is using. So what do I expect here? Because this is another important thing when you do profiling. You start from some expectation, and then you check if your expectation are correct or not, okay? You check if, okay, I believe this is something that should happen. Let me see now if it's happening in reality, okay? So what should happen here is that, again, this profiling is running for 20 seconds. What the Async profiler does is taking 100 samples per second, so and per thread. So what I expected here is that here it should take like 2,000 sample. Okay, so it's 20 by 100 sample per second. And in reality, I have 1902 here. And on this, yeah, and the same thing here. I don't know if you can read. It's 1904. Okay, so it's almost what I expected. Okay, and the other thing that I expect is that, okay, I should just use 2 threads. So I expect that the usage of the CPU was around the 200% because I told Quarkus just use 2 threads. Okay, and so I expect the CPU usage to be around 200%, no more, and I see more here, so something is going not as I expect. And I already know why from the flame graph, because the other work is taken by this stuff that, again, I didn't expect. Okay, so
let's click it so we can show
okay.
Because we have at the base of the stack the thread name. So we can recognize who is the one to blame. And we have this executor thread. That is the blocking thread pool we talked about before. So something is off here.
Okay, so in reality, to understand what's going on is pretty simple. And it's related to what Francesco was explaining here. What's happening is clearly that the REST requests are not processed by the same thread where the request is dispatched, but they are handed over to a different thread. Why it's happening so? Because because Quarkus is doing an assumption, okay? Since you are not returning from this method a reactive object, as you are not returning a future or a reactive object, Quarkus assume that this code is blocking, okay? It needs to do some blocking code to do this stuff. And this is why, by default, Quarkus handle over this request to a different working thread, which is exactly the thing that you are seeing here, okay? The Quarkus arrives on one of those two threads, and where is, of course, you see the biggest part of the netty stack processing the request, and the vertex stuff doing its own work before this thing is handed over to the other thread. Yes?
We can show the people, because one of the good things is that the flame graph is not just navigable through click, but you can use regex to search the part you are interested in. So in this case, let's say that we both know our endpoint class methods, or we know netty, or vertex of the few keywords that we talk about the under the hood dynamics. And then we can search which parts are relevant to perform which work, just to have an idea of what's going on.
So here, for instance, you can see the whole netty part, or you can see the vertex part, because you can...
Exactly, and that's the funny part. So that's the other pitch part. If you search for reflect, for example, that is the method, the method, a key name for reflection, because most of this framework make use of reflection in order to code your code, but actually Quarkus not. So there is no reflection. It's an important consideration, not just because Quarkus is awesome, but it is actually. But that's my lead on the first row. But say that it's an important consideration to understand the performance characteristics of what you are observing. So an additional bit that I didn't told you before, because I was waiting this flame graph, is that Quarkus generate bytecode that is going to call your code. So it's a zero-cost kind of abstraction. It's going to call directly your code, no through reflection. That is important because you won't be able to spot it in this flame graph. So let's now fix it, because we are fixing problem here.
Okay, so what they say is simply is that Quarkus makes an assumption that probably doesn't work well with this specific, very simplistic and not very realistic method. So in general, the assumption, I'd say it's reasonable, it's correct. It's not for this specific REST endpoint, but there is an easy fix. So I can just say that this thing is non-blocking. Okay. So with this annotation, I'm saying to Quarkus, I don't want you to handle this method to dispatch this method to a different worker. Do process this method in the same thread when you receive the request. That's all. Okay. So I can just recompile this stuff.
In the meantime, we can say that we probably won the prize for the longest ever hello world-like explanation. But it's good, I mean, because the whole point of profiling is not just to get data, observation, validate hypothesis, and get a better understanding of how things work, or how much the profiler is broken. So you can have a lot of truth behind this kind of investigation. And now let's check if our assumption that now we are actually using just the IO threads that are just two match what PIDstat is doing, because the other thing that we have done is to pair the Async profiler profiling data with another source of truth in order to see if they match. In this case, is speedstat, that is observing the actual CPU consumption. And is approaching 200. That is what we expect. It's 2 core that are running full throttling. No? Now let's see how the flame graph has changed. No?
So yeah, just to
and
be...
the performance, actually.
Yeah, I forgot to check for the number of requests per second. This
1K
is, of course,
was,
yes,
100K was.
Yes, 100K, so this is going a little better because you don't have all... Can we check before? How was it? Okay, it was 102,000 requests per second, and now we are going a little better. Why? Because we don't have anymore that unnecessary machinery of dispatching the request to a different thread for no reason, but with a cost.
And let me pitch not reactive programming, but the whole thing. We said it's slightly better. It's not slightly better. It's a lot better. Because the actual resource we care about was CPU in this case. Yes. And the CPU before was reaching a lower throughput with about nearly 1 core more. Now with just 2 core, we can sustain a better performance. So the improvement is very relevant. And just by reading the configuration doc, it's incredible. It's always like that, actually. But
so as Francesco said, you can see now that the CPU is reflecting our initial expectation, meaning that the load is around 200, probably at the very first stage. It's still a bit more just because of just-in-time compiler was doing something, or there are some other CPU consumed by the workload, but yes.
The number of CPUs is now 3, and before it was 5.
The number of CPU... yeah, probably here, before it was using actually, so this is an 8-core machine, so probably before it was using 5 of them because there were many threads working, and now they are 3, yes.
Yeah, in this case, we are not confining through CG group or task set the actual execution. So he got the whole full spectrum, of course, of the machine to be used. While instead we were confining the number of threads used by the application. So I have no idea how the operating system decided to move things around.
Yeah, this is up to the operating system, really. But I think it's using as much resource as it needs. So probably here it's using 1 CPU for the load generator, 1 core, of course, for the load generator, and the other 2 for the 2 worker thread of Quarkus. That's what is happening. And in the former run, of course, you needed 2 more. It was started using 2 more because there were many more threads that were spawned and are doing the actual work. So yeah, I generated a second flame graph. Let's give a look also to this. And of course, what you see now is that the situation that we expected at the beginning, right? We don't have any more T stuff. There are only the two worker threads that are doing the work, and the other thing that you should always check, and it is important again, is the number of samples. So yeah. So
there is actually one good thing coming out of this now simplified view of the world. Now we have correctly validated our hypothesis, and now we can even move a little forward. We won't use the whole workshop for the hello world, so don't be worried about it. But the idea is, for example, why do people always say do not run on your laptop benchmarks? Now it's fairly easy to verify. So if Mario search for local, we can check why. It's fun. I mean, it's not fun, but I'm happy when I do it. Oh, okay. orange, it's kernel code. There are special paths to handle local in networking. Though there are plenty of reasons why you shouldn't. The reason why we do it is because we know that what we have created as an experiment is relevant to still be observable despite using a local host. But the point is that you can check these kind of things. It's not just to spot issue, it's to understand systems. Okay, so that was the main take.
Okay, so yeah, and the other relevant part, as I was saying, is that you still verify your assumption. So what I said before is that I expected around or a little less, of course, than 2,000 samples here, because it's running for 20 seconds and it takes 100 sample per second. So yes, you can see here that this is really close to what I expect for both the worker threads. Is there any else?
No.
Okay.
We can break another program.
Okay. Okay. So I don't know if we want to run another example, or do you have any question, by the way? Yeah, let's try to do this in an interactive way if possible. So do you have any question at this point? Okay. Do you want?
Or we are really good, or we are confusing
yeah,
everyone.
I don't know.
Actually.
Yes, it's always yes. I don't know if we want to make a break now, Francesco.
Yes.
We want to make a. It's
I saw
okay
a couple
for you
of
to have a break.
Tired.
Okay. So let's have let's say 20-minute break, and we will start 2:50. Okay. Thanks.
You created the hype, because and now hello world and break.
So during the break, we got a few questions about simply I cloned your project, it doesn't work at all on my machine, okay? And yeah, we forgot to mention this in reality probably, and they asked me if it was a JDK issue, which JDK I'm using. By the way, I didn't say this, I'm using the JDK 21, but with the right operating system, this thing should work with JDK 11 and up to 21. Probably, Francesco, you don't want...
You're pretty biased to say right operating system.
Yeah, well, I mean...
The best for this kind of analysis.
Yes, the best for the work at end, let's say. Okay.
Exactly.
Maybe, Francesco, you want to clarify what's the problem?
It's just two tiny points. So the first one is that, let's say you have macOS. macOS and perf events doesn't marry well, because actually they do not expose that one, that API. And for this reason, it means that you can collect a specific type of events. And not only. The other thing is that the way by which Async Profiler works when you can't collect perf events is by using another mechanism called iTimer. iTimer exists from long time on Linux. It's kind of broken if you have too many cores and you are hammering your CPU with CPU work, so you can miss a few samples. But the good thing is that it's an open source tool, so if you search in the issues, you will see myself complaining about it all day long. And Andrei is very wise and calm and say, it is what it is. So you should be aware of it. Let's move on.
Yeah, so is there any workaround for this? So what people with macOS can do, or
buy a Linux machine? No. I wouldn't. I never say that one, really.
No, but I must say that for Windows machine instead, there's good news, because we tried the emulator. Yes, we tried the Linux emulator inside the Windows machine, and I must admit, we were surprised of how good it is. I mean, it's working right.
You are too sincere, Mario. That's the problem.
Yeah, okay. we tried hard to make this work with macOS, but in all honesty, we couldn't. So
No.
yeah.
No.
Okay. So let's give a look to a second example. I have another REST endpoint. It's another quite simple one. The only thing is that I have a time service that we will see later that I'm injecting inside my REST endpoint. And then I'm using it. So this is just a service to provide a tick service, a tick mechanism to say, okay, what's the current timing? And it delegates to the service time to calculate the timing, and that's all. Okay, so let's give this a try. Okay, so this time, as I said, in our script, the default is to hammering the hello world endpoint. We are going through a different endpoint now. So what I'm doing now is simply say, okay, use as URL this time endpoint. Okay, and that's all. So I can run this benchmark again, and as you can see, it is calling that endpoint that I mentioned it. Okay, so let's see what happened, and let's try to figure out together what's going on, right? Because this is what you typically do. I didn't show you the time service. It is a black box for us at the moment.
We have, let's say we have just a documentation
Yes.
that very high level told us that is an external service which have a specific quality of service latency. We know that is rate limited, is concurrency limited as well. And that's all. We don't have much more control. And the granularity of the tick information are at second level. No?
Okay. So let's see what happened here. The first thing that we can notice is that the usage of the CPU is really, really underwhelming. Okay, and also the number of requests per second that I can serve is very disappointing. I mean, with that other very simple REST endpoint, we saw a number in the range of 100,000 requests per second. Now we are serving less than 400. So, yeah, something is not very satisfying with this service.
Yes.
And we would like to know why. Okay, so let's try, as usual, to give a look at our REST endpoint, at our flame graph here. Okay. I hope you can read this.
If we search for event loop, for example, we will spot on the right the two event loop of vertex. We have in the middle the one about the blocking thread pool, because we didn't use a reactive asynchronous type. We didn't put the non-blocking things, right, because actually is a blocking service. So it's fine that we run in the blocking thread pool. And we are spotting something weird. The weirdest part is that if Mario search for compiler, it will spot in the left the yellow part that we said is related to just-in-time part, specifically the compiler. Why is that so? We say that the whole experiment is 40 seconds long. And by the number of requests per second and the low CPU usage, we are expecting that we are not calling enough our code to make it hot. And that is definitely a problem, because relatively, we didn't check yet the number of samples, we can say that is pretty relevant, the compiler CPU usage. Is nearly as relevant as the one on the blocking thread pool. But as we said, is a relative problem, because the other thing is that if we look at the number of samples, we can see that there are very few. So few that probably won't matter what we do there. So in each example we made, there is a different lesson to learn. Here the real problem is that we opened the CPU usage thing, the CPU flame graph, because it's not a resource we care about, because it's not the most consumed one, probably. And by looking at the percentage of CPU usage, probably would be enough. So we can be curious and look what's going on, but actually it's not relevant for the performance characteristic of this system. So let's try to check what is the actual resource we care about in this case. And it's the wall clock profiling, the time it takes to perform the actual service we are requesting. So let's try to use a different
Okay, yes. So
way.
before moving forward, let me clarify two things that Francesco mentioned it, but I want to make crystal clear. Okay, this now, as in the very first example, we are dispatching our request to a different worker thread, but this time we want to do this because we are calling a blocking service, so we don't want to block the, you never block the event loop, right? Okay, and this is one thing, so this is expected. The things on the left is the work made by the C2 compiler. Okay, so in this example, you see this thing there because this thing is running so slowly that C2 didn't see enough usage of our service in order to optimize that part, and so it's still doing some work. The JIT compiler is still doing some work while the actual profiler is running not in the warm-up phase, but in the actual sampled phase, okay? And this is normally not what you want, okay? I said in this case, it's caused by the fact that our service is running very slowly, but more in general, when you see that part, the other reason why you could see that part, which is very, very relevant, is that you didn't run a long enough warm-up phase, okay? Of course, I could run a longer warm-up phase here and not see that part anymore, but this is not the point of this specific benchmark, because my problem now is that the service is running too slow. But in general, if you see that, if you see this, just to be clear, this C2 thing, that is the C2 compiler, it's a JIT compiler. The warm-up phase is not long enough. There are some still JIT doing some work optimizing your code, so you should rerun your benchmark with a longer warm-up phase, because what you are measuring is not correct. That's all, okay? On one side. On the other side, there are situations maybe when you don't want to measure a system after the warm-up phase, okay? You really want to measure the startup performances of the system, and this is a totally different kind of work, probably even more complex. I don't know if Francesco wants to say something.
Complex in this case, because you have all the environmental effect of not having the code really warmed up, and you should account for that. So the interesting bit is that you can have this information about how noisy are the presence of the runtime in very different ways. In this case, we have a single tool to rule them all. But in different cases, you can make use of JFR or collect compiler logs and still be aware that something is going on that is disturbing the performance characteristic of your application. And you would like to understand how much is disturbing, okay?
Okay, and as Francesco said, the other point here is that, okay, we are gathering some samples of our of the performances of our REST endpoint. But in reality, this is not really relevant. As I said before, for that specific thread, I am expected something close to 2,000 sample, and I have only 66 there, sorry, which is really not relevant enough. I mean, I'm not really measuring what I would like to measure. In essence, this flamer graph is garbage, okay? This happens. Probably we should educate people also to this. You don't need to interpret a flame graph at any cost. Sometimes the only interpretation you can make is this thing is garbage. I should try something else that is more significant for my use case. That's the lesson for this, the main lesson in my opinion for this thing. Okay, so what we are saying is that the CPU sampling in this case is not telling us much, so we should resort to a different kind of event. We would really like to know now not where the CPU is busy, because that's a problem. The CPU is never busy enough, okay? So what we want to do now is really measuring the whole clock, where it's wasting our time, okay? So I'm rerunning this thing again, but this time I run this with, I don't know if you can read.
Wall with the A.
Sorry. I'm running this with profiling not the CPU sampling, but the whole clock time. Okay, and let's give this another run. Okay, of course, the result you will see there. We didn't change anything in our code, so the result you will see there will be the same. The number per request will be the same. The occupation of the CPU will be the same. We didn't change anything. What we changed is what we are measuring.
Exactly. And for the wall clock profiling, a SIM profiler, given that we are not hiding the under the hood behavior of the tools we are making use, is not adopting a fixed frequency kind of collecting of data. So it's no longer 100 hertz per second per core, but is starting with 10 and depends by the amount of thread created. Why? Because in the previous part of this talk, I told you about the challenges of a wall clock profiling, in which you risk to have a huge pool. And the fact that you subsample even threads that are supposedly to be idle most of the time or not doing anything, you risk to not have accuracy of information. So Andrei changed slightly the Async profiler engine in order to change on fly the frequency depending by the amount of living threads that are going to be sampled. So in this case, we are not looking at the sample numbers like we are used to, but the relative behavior is still important. So the very first thing that we can observe by this flame graph is that, too much information, actually. But the too much information is coming from our laziness to use the default behavior of a Async profiler, in which, as I told you, we will observe even threads that are not doing anything, because actually a Async profiler doesn't know. So let's check, for example, G1. G1 is the default garbage collector, and we can see that in this case there are 3, 4 G1 threads that are not doing anything relevant because there is not enough load. We can make use of other part of the Async profiler tool to filter out the thread based on the one we are interested in. But in this case, we are not hiding this information because we can navigate pretty easily. There are not so many threads. But in the real world, with 1K thread pool threads, it's better to filter, actually. So we know the package and the name of the time service, right?
So let's start looking for it, yes.
So we can now search for some relevant package and see where we go.
Okay, so this is, I I'm just looking for the name of the method that is serving the REST request. So that's the easiest thing, and it's here, right? So this is the actual
Let's
code.
click it and see.
Okay, so let's pick one random one.
So
And,
as we said, we were faking the actual code.
Can you read?
No.
Okay.
Okay, as we say that we were faking the actual code because there is no real-time service. And we now know the under the hood incredible and awesome detail of our implementation. That is indeed using a semaphore to limit the concurrency. And we have performed a very handy time sleep to imitate, emulate the network activity. And now the funny part. Okay, so we can see that the larger, the more the time is spent doing things. So we know that's important. And everyone will say, okay, wait, what's the bug? I mean, there is a performance bug. No, not really, because sometimes you profile to know more about your system. Sometimes you profile to reduce the overhead of what you have implemented. And sometimes is to perform different design decisions. So in this case, we have observed the system, but actually looking just at the source code and the hints about the limit of time service, we can make a better engineering decision here. And it's not actually a performance. It's a performance improve, but come with a different direction of how to make things better. In this regard, we can follow the really simple rule that put a cache and solve the problem. Actually, we put a cache and solve the problem. We said that the granularity was 1 second for the time service.
Just to be clear, through the flame graph, we are discovering the internals of this service thing, okay?
The magic has disappeared.
Yeah. So we assumed that this time service thing is something that we use that we cannot change, okay? We are just discovering, we probably read some documentation about it. The documentation was outdated, I don't know. But in reality, what we discovered is that this timer service use a semaphore very likely to limit the parallelism, how many thread can do the request. And of course, yes, there is a sleep here through which we are simulating the time that internally it takes. So now we can probably give a look to how we implemented this timer service, that it's the things we are describing. This is quite common actually, to use a semaphore to limit the number of parallel requests that you can serve. And yeah, of course, there is a blocking queue here that is making things even worse. But surprisingly, it's not the sleep domain source of waiting, of resource consumption, but it's the semaphore itself.
And the reason comes from the initial explanation about the workload, because we say the 10 connection is just for the semaphore. So at least we have 6 waiting every time. And given that is for the semaphore and we wait for 10 milliseconds, we couldn't expect anything better than 400 requests per second. That is matching our expectation. You would think that is really a fake kind of example, but actually
it's
pretty real,
yes.
Because you often have other services you have to communicate with, in which you pay for a specific resource you care about, and you don't want to overwhelm them, because the rate limiting sucks, and often the time you pay more than you are expecting to do. And that's why in this case we are making use of different solutions that employ caching to solve both problems. So we will solve the problem of rate limiting, and we will solve the problem of being blocking and misusing this native thread. And using Loom is not a solution. I don't know if Nicola is here. Maybe. No.
Okay. Yes. So yeah, the idea is pretty simple here. Of course, we have a resource that it's limiting the number of threads that can access it. maybe for a very good reason. So what's the fix? The fix is that we can just cache the result. I mean, we just need to update the time every second, and we can do this with this very simple annotation here. So this method is simply called every 1 second, one single time by one single thread, which is the scheduler thread this time. That offline, let's say, will update the time read from the service time, and we are just serving it, which is like cheating. I don't know if we want to say this.
It's always cheating.
Yes, okay. But it's how caches work, okay? So it's really the right solution in this situation. We have a service that we are hammering, and the service that we are hammering cannot keep up with the number of requests that we are sending. And by the way, probably the service is also making us to pay for each and every request, so it's even worse. Yes. So this is one more reason where you may want to cache the response. Okay. So let's see if this trick works or not. I can rerun this. Do you want to do the wall clock thing or?
No, it's fine with CPU, and we will spot in the PID-stat output that we make the right choice already. So we cut the time, and we still, if you think it's fictional, just replace hibernate with the caching in your mind. It's not that different, actually. It's the same thing. You're paying for network, you pay for CPU time, put a cache. I mean, if you don't need the most up-to-date value, obviously. So this is kind of pretty relevant and simple way to show what happened under the hood when you make this kind of design choices.
Okay. We can already say that it's going much better now from the CPU utilization rate. The
request per second.
The
request per second will be different.
Is still printing the So yes, of course, now we are above 100,000 requests per second again. So yes, the fix work, the cache works. The main takeover from this example, I believe, is that you use the flame graph to explore what's going on. I mean, the fix is obvious. Figuring out where the problem is, it is not that much obvious. Okay, of course, I have one single service that I'm calling, and I know in advance probably that the problem is there, but think to a huge system. You have a performance problem, and you have no clue where the problem is, okay? Or even worse, you have a clue and it's the wrong one, because you didn't measure.
Yeah.
So you actually do measure, you find where the problem. Otherwise, you have 10 services and you are caching all of them. And for 9 of them, it's useless. And you are overcomplicating your architecture. You are providing a not so fresh result because you are caching it for no value at all. Okay? But you have 10 services. One of them is not able to keep up with the amount of requests that you want to serve, and that is the only one where you want to use a cache, not everywhere. Okay.
Rate limiting. I mean, you can use different mechanisms, but the point is that indeed to observe the system always.
Right. No? Sorry. Okay. Of course, the point is that you can use lots of simple or more complicated workaround and fixes to fix the problem. The point is, let's figure out where the problem is.
That's the most difficult part, actually.
Yeah, right.
So, and we can move to the next example. That something that
well, we can show the flame graph if you want.
It will be. We can make an hypothesis even now. So the number of requests per second is approaching the hello world. So I won't expect that much difference, right?
Yes.
So number of samples is indeed around 2K for each of the single thread. Everything is running on the IO thread. If we are curious, we can search for now or cached, or I don't know what's the name of.
Yeah, now.
That's another pitch for
But
Quarkus.
I don't know if we can spot it somewhere. I mean, now it's taking the
0.64.
0.64%, so it's very hard to tell
Exactly.
where it is.
And it's fun because in theory, that's another reason why we should always know a bit of the internal of the things we do. No, like knowing that a car got tires, you know. In this case, we know by default that the JSON transformation is plain text or JSON output. I don't remember.
I guess it's plain text.
It's
No,
JSON.
It's
So
JSON.
in theory, it should use Jackson.
Yes.
So if we search for Jackson, we can see the effect of using the JSON encoding. And the thing is that it's pretty relevant,
yes.
you know, but still not as much relevant that changing the performance characteristic of our system if compared to an hello world. So sometimes you look at things, you say that's a problem, but you should look at the numbers. So when I was younger, my teacher say, okay, you got a number, is the 8, the 8 is negative. It's fine. No, it's not. It's wrong. So the absolute number, how things behave, is pretty relevant. Never trust a single source of truth. That's the other point, no? Because there is no truth, actually. So let's move to the interesting one. It's interesting, the next one, because it's coming from a real production code that I won't tell where it's coming from, but it's usually from the worst problem in the world, logging. Who cares about loggings?
Yeah,
Will be
and
fun.
why it should affect so much performances? Yes,
Yeah.
it shouldn't happen, right? Or
No, it shouldn't.
not that much. Okay. So yes, what we have here is that we faked a repository of person, which is as usual injected in our service in our REST endpoint, and we want to query this repository with a specific number, which is supposed to be the age of the person. So in essence, we want to find all the persons with that given age. Okay, so we want to be returned with the collection of the persons that, for instance, has 42 years. Okay.
It's in memory.
Do you want to show something more about this? Or
it's an in-memory repository.
Okay.
We know that because we have the non-blocking things, so we assume it to be super fast, super cool, non-blocking, whatever. And we can take a look what happened by clicking on it. So with the age equals to what it does, we can show it, actually.
Okay, yes.
But
what
very
I
quickly.
forgot to mention is that I annotated this with non-blocking. So what you expect now is that you don't dispatch this request to a different thread. It will be served by the main worker thread.
Yeah.
Do you want to?
The code is fine to show. There is no spoilers in the code, actually. That's why we are syncing. Because
Okay. So yeah, we have this repository that is pre-populated with this list of person, and a person is a simple record where we with this method age that calculates the current age of the person start from its birth year. And what the service just does is traversing the collection, yes, doing some logging and finding all the person with the requested age, and returns the collection of those persons with some more logging here. Okay, that's all. So
Finest logging, that's important.
yeah,
So
okay,
it's-
yeah, but don't spoiler this. Let's see what
No, no.
happens. So what's the name of this endpoint actually? Okay, person age.
42 is not by accident. It's my age, actually. So it's not a magic
Well,
number
it's
of,
it's
you know,
also the answer for everything. So
by accident.
yes. So okay. So let's give it this a try. As usual, the first thing that we can check is the first two things that we can check is the CPU utilization rate, and the other thing is how many requests per second we are serving.
We are fairly using
Okay,
the speed.
so we are doing pretty well on the CPU utilization rate, meaning that we expected something around 200%, because as usual we are using two threads. And as I said, we annotated the method with that non-blocking, so we don't expect it to dispatch to a different thread.
There is another information in PIDstat that is, we should capture it. We do have not just the overall CPU usage, we have the I/O one, so the one spent on networking call and things like that. In the previous test, there was nearly evenly balanced between user and kernel. But in this case, it's not. It's 170, the user one, and 29, the I/O one. That's interesting. So it means that there is something we actually do that is consuming that CPU. It's not just an effect of what we do. No, it's... But let's see the flame graph. And the
Okay,
final number, too.
Yeah, the other thing that we can notice before it's, of course, as usual, the number of requests per second that we are serving. We are a bit below 30,000 requests, which is not great given what we saw before with the former benchmarks. So let's give a look at this flame graph.
Yep.
Okay.
Okay.
So let me make this.
And this is kind of match our expectation by reading PIDstat. So the kernel I/O one is not just that one. What with localhost we can expect to be the most of it is the orange part. And we saw that the balance was mostly on user code. So the green one and the GC, JIT, whatever, is not kernel code. And indeed, if you look at the colors, you will see that it's mostly green. So it's something dependent from what we do. So it's a good match. We can even check the number, but will be longer for no reason. So trust me. Or not trust me and send me an email too.
So let's look for this the method serving this REST endpoint inside our flame graph. Okay, it's here. So maybe I can click here to enlarge this thing and try. Yeah, this is actually what happens when I call the REST endpoint, and we should spot at first sight where is the main culprit, right?
And the first confusion comes from the name of the methods. That's the reason why the people that love virtual thread usually advocate against asynchronous programming or reactive programming. We were using streams. And the streams are separated in two phases. You have building, the part in which you build the pipeline, the one in which you run it, the pipeline. When you build it and when you run it, they are separated. So it means that in the flame graph that captures just the running part, you have a very ugly name that doesn't relate easily sometimes with the builder part that you expect. No, that's an important and sad fact. No, indeed there is the lambda used.
Okay. So what we discovered from this flame graph is that calling this login service.finest method is consuming a lot for no reason, right? Because in the output we are not logging anything. This should be free. I mean, I'm not doing any log really. So why this is consuming so much CPU resource? The problem is that as you can see here, okay, once again, we are assuming that you are using an external, well, not service, but probably library in this case. Anyway, you are using some alien code, some code that is not really part of your application, this time to do some logging, okay? And now with this flame graph, you are discovering that probably the implementer of this logging framework, this logging library, did something wrong, okay? Because it is formatting the string to be logged even if nobody's printing it, okay? So yeah, let's spoil this. Let's see what happens here. So in essence, I'm calling this method, and as you can see, yes, the implementer of this logging service did something not very clever, because it is correctly printing the string only if you enabled the finest logging level, but it is formatting the string regardless if it is printed or not, which is the thing exactly that it's eating our most CPU time, okay?
And that means that every time you print line for real using formatter, that's what's going on under the hood. So it's not fun, really. In this case, it was a bug, actually.
Okay, yes. Anyway, as I said, we at least used the flame graph this time to find where the problem was. We are using this logging service. So again, in my hypothesis, I'm saying that okay, of course the stupid things will be doing this, right? But as I said, this is an external service or an external library for me. So let's suppose that I'm not allowed to do this, okay? But now at least I know where the problem is, and I can work around it, okay? So the only thing that I can do to work around this problem is using this method. The only thing that I can do is, okay, asking to the logging service is if I'm at logging at the finest level, and if I don't call the logging service at all, okay? Let me try to do this. And well, the the other complication is that I'm doing this inside a lambda, so it's not the nicest possible way of writing this, but maybe you can abstract this a bit, but okay.
Still look ugly.
Yeah, it works. It looks ugly, sorry, but yes, at least it works, okay? And of course I can do exactly the same thing here.
Even outside.
Sorry?
No need for each. You can do it. You can avoid the for each at all.
Okay, yes. Yeah. You're right. Yes. Okay, as I said, this is not the best thing, but since I'm using this bucket logging service, at least I know that the problem is there, and this is the only thing I can do. Okay, here I'm missing a semicolon, of course. Okay, should be fine. So let's try to recompile this thing.
And in the meantime, misuse of logging API is pretty common, really. And the point is that you don't have much control to change things. Even if it's open source, sometimes you gotta use it in the right way. So if you have a profiler that suggests you that it's not good what you have done, you can make your code uglier if it really makes sense, no? Based on the number you got. It's always a trade-off. In this case, the numbers were pretty low, so that's why we choose for that. Okay, something has already changed. The user time was 170 nearish before. And the system time, system CPU time was nearly 35 or something like that. Now we have improved, no?
Okay, this is the old one, if you want to compare.
Okay, so something has changed. The user code seems to require less CPU, and there is more kernel and I/O activity involved. That seems already a good thing. Let's see if the request per second already shows something.
So this is the old run without the fix to the logging call. Yeah, we were above 30 key requests per second, and now we improved a lot, yes. Still not ideal, but we improved a lot. But maybe, yes, this is another quite typical thing when you do profiling, right? You find a first bottleneck, but by fixing it, you probably find a second one and a third one. Of course, the first one is some way hiding the effect of the other, but the one you fix one, then it will see clearly the other. This is another quite typical thing. So what you do is improving the performances of the application with continual iteration. So, okay, this is, by the way, a mistake that I did in my early days of profiling. I do one profiling, I generate one flame graph, okay? I fix something, I see the effect of the fix, okay? And then I think, okay, let's see if there is one more problem that I can fix. But I didn't generate a second flame graph with the changed situation. I was looking for a second problem in the very first flame graph. But at that point, with the first fix, the situation is totally changed. I'm seeing something totally different. So if you, the other lesson to me here is that I changed something. I cannot reuse the flame graph that I generated before the change, because the situation could be totally different now, okay? Okay, so let's see what's going on now. Okay. So what can we notice here, Franz?
This is pretty interesting, especially if you have the chance to search with the phone VDSO. Go to the top, Mario. It's exactly on the top. You can just click and you will see the red one on the top. So every time you interact with the specific intrinsic or Java method, like system nanotime, current time millis, you are asking something to the kernel, actually. And there are many ways by which these things could be improved. Usually the user shouldn't care about this thing. No, they should. And that's why the flame graph work pretty well with that. Because they can show you the cost of calling here.now. That seems irrelevant, but it's 60 requests per second, while we know that we could achieve like 60,000 key, while we know we could achieve nearly double this digit. So in this case, it's relevant. And we can check the internal details of it. So if Mario click it, you will see till VDSO, that is a memory region shared with the kernel, in which in theory application can extract data provided by the kernel without incurring any syscall. What's interesting is that it's so relevant, this workshop, that on the cloud, if you have an unstable clock source, that became a syscall. And that can be super costly. And if you don't use the right profiler, you won't spot it. You need the right profiler to show things. So in this case, it is still costly, but could be worse. So that's why it's a suggestion to perform this kind of analysis. And you can search in Wikipedia what it is, because it is exactly what you can read out of it. So we have some call of local date now in the record, right? Yes.
So, what we are saying is that okay, now I'm focusing on the method that is serving my REST call. So I only expect maybe only Java call, and if you use a different kind of profiler, you will see only the Java call. But the problem here is not on the green or the light blue part. The problem here is in this red part that I probably don't expect, or I don't expect in a so relevant portion. So what I wanted to underline here is the importance of having a profiling that doesn't show you only the pure Java side of the story, but that shows you in its entirety what happens in your machine. Okay. In this case, we are issuing tons of kernel code that we may want to avoid. That's all. Okay, and also, of course, the flame graph gives me a clue of where this call it is here, because it was something that looked pretty innocent at the beginning. I'm calculating the age of the person, but if you remember how I'm calculating the age of the person, sorry. If you remember how I'm calculating the age of the person, every time I'm asked what's the age of the person, I'm doing this kernel call to know the current date, okay? Which is really wasteful. I mean, the year is not supposed to change every nanosecond. So the obvious thing here is, once again, yes, that's the default answer to this kind of problem. Let's cache it, right?
Again.
Yeah,
Yes.
again.
The two most powerful optimization, removing code and caching, and you're done.
Preferably remove code.
Better, huh?
Yeah, it's the best one. And it happens quite often, I must say. Okay, I say, this is another very typical thing. Sorry for the digression. You broke your head to say, okay, I have this code, I want to make it faster. How can I make it fast? How can I make it fast? And at some point you discover that you didn't need it at all. So it's really the king of optimization is you don't need it. Okay. Unfortunately, now we need it. We need to know what year it is, because given our domain, we just know the birth year of the person, so we still need to calculate his age. So what we can do is just doing this.
It's convenient. So in theory, we should update it each year, blah, blah, blah. In this case, instead, we can even cache it just once for the sake of looking what could be the performance if things would work without that code in the auth path. So calling for the years every time.
Okay, of course, this is not
production ready.
Production ready, yes, let's say so, because at least we should refresh the year every year. But we just want to prove a point here. We just want to prove that the problem was there and we are getting rid of it, and we can then maybe improve our code with something more production ready in a further iteration. Okay, sorry, I was of course forgetting of recompiling this thing.
That's the other source of performance.
That's the other thing that happens quite often. You're changing a lot, you rerun the benchmark and nothing is changed. Why? Okay, I forgot to recompile. Okay, so let's give this one more try. And let's see.
Yeah. In the meantime, I would like to reiterate what we are doing. So performance engineering, whatever it means, is always assumed as a form of engineering, but actually it looks like more physics. So you are a scientist, you have an environment, you have a hypothesis that you would like to verify, and you screw up everything with a not clean enough environment. But it works exactly like that. You should be aware of it, reiterate, change things, retry, measure, and see what happens, and makes new hypotheses. That's the scientific approach. It's an empirical kind of science, no? And you don't need a role for that. That's why I'm saying, no, performance engineer, it's just a name. You can do it. So that's what we are doing in the workshop on our laptop. So incredible.
Okay.
So numbers are completely...
Yes. So let's give a look. Both the utilization rate, yes, the CPU utilization is good as usual, but this time we are using less system resources, and yes, this is the most important thing, of course, the thing for which we are paid for, right?
And I'm surprised, actually, because I have personally a bias. How many people love streams, Java stream? You are better than me, actually. I hate them, because I know that create a lot of garbage, polymorphism, all the worst thing. It's a wrong bias, because the reality you should measure. In this case, the code, the business code is way more complex than just returning an hello world. But actually, in this specific experiment with that load, the numbers suggest that we are deadly wrong. So it's not that bad, actually.
So to reinforce what Francesco is saying, the starting point, the starting reason why we wrote this benchmark in this way is that, okay, let's demonstrate how bad the Stream API is performance-wise, okay? So we pushed this hard to do this thing, and we found that it really doesn't matter, really. I mean, it's working really well in this thing. I mean, I could rewrite this thing with a plain for loop, and you will see that nothing changes. I mean, the bottleneck is not here. So we assumed that the problem was there. We try hard to convince ourselves that the problem was there, but it was not. Okay?
So we do not write just ugly code. Sometimes.
No, well, yeah. That's another thing that I discuss quite frequently with Franz, because I have some, it happens that I have some underperforming code. I don't have a clue on how to fix it, so it is the business, usually the work of this guy, and I hand it over to him, and it gives me the code back, and I don't have a fucking clue of what that code is doing now. The problem is that, yes, sorry, Franz,
No,
but
it is what it is.
okay. And guess what? Yes, it was as fast, but now I have no clue what's going on. So I have to study how it works. I have to ask him how it works. The point is that there is a trade-off, okay? And the trade-off, sorry if I go back to this. The trade-off is exactly here, right? Is in the 3%, okay? That's really, well, 3 probably is not the right number. Could be 2, could be 5, but you get the point. And yes, sometimes you are obliged to write ugly code because in the bottleneck, you don't want to pay the performance cost of, for instance, a megamorphic call. So instead of having a nice interface, you are casting to, yes, pretty okay. But you do this only there. You this only in that 3% portion of your code. You don't do the same on 100% of your code base, because the benefit will be, the performance benefit will approach to 0, and you will make 100% of your code totally unmaintainable. Okay? So my policy is I want the 3% of code that only Franz can read, and I take care of the remaining 97%. Okay? And the hardest part, again, is, well, the hardest part is finding somebody like Franz. Once you have found it, the hardest part is the hardest part is finding the right 3%. Okay? And block Franz on the remaining 97, which is also hard.
The optimal stop problem.
Yes,
you know?
yes. At some point you stop. Okay, sorry for the digression. Let's give a look. Okay, we saw that we are going much better now. Maybe we can give a look at what's going on with this latest flame graph, but probably I believe we wouldn't find anything that relevant now. I mean, it's going as expected. The number of sample is a little shy to 2,000, which is what we expect as well. And we can look for again for the name of the method that is service our stuff, but probably it will be very tiny now. Okay, it's here. Okay, so it's, yes, now the culprit is the stream, right? But in reality, okay, so this is the level when you stop Franz to turning the stream into a for loop, right?
At best.
Yeah. Okay. So, yeah, I'm making fun of this, but this is really our workflow, right? This is, yeah. So you find a good balance. So the point of this deep dive is bringing our experience on the field, working on this stuff, right? Okay, in a simplified way, in a constrained way. But it's not always that simple.
It could be your little, dwarf in your mind that say, keep on doing it, and you stop. And you say, okay, it's fine. I achieved what I need to achieve. And the data show that. That's the important bit. In this case, we are separate, but it could be the single person, actually.
Okay, yes. Well, I planned to do 2 breaks, but I don't want to make one more break and then give the last example. So probably we can do, if it's okay for you and we are not killing you, I think we can do the last example now and then maybe finish 10 minutes earlier, right? Yep. It's okay? Okay. Let's start from
The not fast random generator.
Okay. This is the latest example that we want to show. You want to comment it, Franz? Okay, let me
We are
make
still
it more
stuck
readable.
with this stream thing.
Yeah,
as you can
okay.
see.
We wanted at any cost to find a problem in the stream. Okay, go on.
Moreover, we even boxed integers. That is horrible.
Yes.
I have nightmares for days. So we are generating number according to a specific argument coming from the network. It's using text plain, so there is no JSON involved. But as you can see, with very tiny, small things, it doesn't matter that much. And we are creating a lot of stuff. So we are boxing. That means that an integer things became a real thing, an integer instance. An int things became an integer instance or long. I don't know what type is. We are using string value of, that is creating string. And we are collecting them. So we probably produce a single string by the end. So it's just a garbage generator. No, it's actually have a business purpose, and it's using strings. But the random service, according to the non-blocking annotation, is fast enough or reactive or whatever you think would be the good name for that. But the point is that it doesn't require to use a blocking thread pool again, so should be decent enough. Okay. So let's see what happens if we run it. And we were really...
Okay, so in essence, with this invocation, I'm generating 10 random number, and I'm concatenating all of them in one single comma separated string. That's all. Okay. So I don't need to recompile now, no? Okay.
No.
I can just do this. Okay, so I'm calling that rest endpoint now. Let's read the stats again.
And given that we are still waiting until the output is produced, the fact that in the previous example we were looking if logs were produced, it seems a very natural practice to see if there are effects in the real world of the things you expect them to happen. But there is an actual name for this methodology. It's called use, if you are curious about it. Has been written by Brendan Gregg, that was a performance guru in Netflix, then later on Intel. And the point is that if you have a system that basically don't do what you expect or produce errors, you shouldn't make it fast in that thing. You should check first what's the problem. So the performance issue comes from an healthy system, and you should be aware of that one first. No? Oh, it stopped. Okay, yes. The numbers are not that bad, incredibly, it's...
Yeah, there is a lot going on here. The random generation could be costly, but in reality, we are not seeing these bad performances, so we are pretty happy of this. But there is somebody clever, of course, in your organization, and it says, okay, this random generating thing is not fast enough. I know that there is a problem here. Yeah. I don't know why, but he knows that there is a problem here. And he wanted to make it faster, right? So, everybody knows that the secret to make us a method or a service faster is to prepend it with the fast prefix, right? You write fast and it goes faster, right?
Yeah.
Okay. So just to be sure, I fixed this thing. Okay. Of course, I use the same prefix also on the rest endpoint. What I'm doing here is that, okay, I'm assuming that what is costly in this method is to create the string, okay? Is to allocate the memory space to do the string concatenation, Okay, so what I'm doing here is that, or my clever colleague did, is creating this new utility service that is injected here, which is a pool of strings. So I'm creating this pool. So I in this way, I'm no longer obliged to allocate the space to the space to concatenate the string each and every time, but I'm taking it from the pool and I'm using it, and this is supposed to be faster, right?
And it's not boxing, because the string builder in its API got append with the primitive type, so we don't even need to box anything, actually. So it's supposed to be faster.
Okay. And I'm also not using anymore that stream
ugly lambdas.
The stream API, because come on, it's not performance enough, and we are happy with this, right? So at some point, the clever colleague put this thing in production, and we all expect to see how fast it is, right? So let's give this a try.
Now let's observe as before. You know, the balance before were that most of the code wasn't, the most of the percentage wasn't on user. It was evenly balanced between network and user. While here, not again. So it's still pretty unbalanced on the user side, but we should check what it was before. I could be wrong. I'm often wrong. So, but the request per second will tell immediately the truth. It's thrilling. We can always make it 10 seconds, but 20 is...
Okay. So...
Worse.
Yeah, something went wrong in the making of this faster service. We were above 100,000 requests per second before, and now there is something going wrong, right? And okay,
we know
let's try to figure out what's going on wrong as usual.
We won't repeat all the previous thing, but we know which resource we care about because we saw that we are consuming the whole CPU time. So we would like to check what happened there. No?
Okay.
And it's pretty bad.
What can we notice here, Franz? So
okay, so the supposedly fast generator got the bug because it's code got bugs. In this case, probably, given that it's a pool, pool can be made of two different methods: acquire, borrow, whatever, and release, in order to get it back in the pool. But it's more error-prone because you have a two-stage operation. And sometimes you can forget to put the finally and release memory back to the pool. So what has happened here is that in the acquire part, we have the generation of the string builder of a certain size, very generous, because it was supposed to be pooled, but is not pooled. So it keep on getting allocated. Why we should care about related to CPU? What are the interesting facts of this data?
Yeah, so in reality, yes, Francesco spoiled where the problem was, shame on you, but what we notice here is that the purpose of this pooling thing was avoiding to allocate, and as you can see here, we are allocating even more than before, so something went wrong there. But this is a CPU sampling frame graph, and the problem is on allocation now. Or we wanted to fix the problem on allocation, a problem that probably didn't exist at all as we saw, but whatever. We created an allocation problem now. So yes, this flame graph is telling us something, but probably since the problem is not on the CPU sampling, but it's on the allocation rate, maybe a flame graph that shows us the allocation could be even more revealing than this, right?
Exactly. And
so
in the meantime, Mario provided the allocation event flame graph. Regarding the previous one we saw, why should affect CPU time? CPU usage. It's weird if you think about it, because the usual story that we tell to user is that if you allocate something that is going to be in young generation, who cares? Indeed, we couldn't spot any GC heavy activity on the flame graph. So it is kind of real. It's cheap to allocate. But at the same time, if you allocate something that big and you have to zero it everything, because the memory you give back to the user should supposedly be cleaned, then you pay the cost of cleaning up the whole thing. It's part of the cost. So the good things of using the right profiler is that can spot even that kind of problem. That is a part of the story of the allocation thing. Related allocation, at the beginning, Mario talked about different type of profiling. No, you can have event-based, statistical, that are the sampling one, and instrumented or tracing. One of the nicer thing of Async profiler is something that exists in JFR as well. It's to spot two type of allocation events. One is called new TLAB allocation, within TLAB allocation, and out of TLAB allocation. Okay. How many people knows about TLABs? Okay, oh, poor boy. No, I'm just joking. It's a very useful information. Basically, the GC to speed up, different type of algorithm, actually, of GC, to speed up allocation, make use of thread local arenas. These arenas can grow slightly in size and capacity, but at a certain point, the GC cannot grant you in unbounded memory to be used within the same thread, to be quickly allocated, because the whole point of it is to get faster allocation. So thread local are faster to perform allocation. But if you exceed the allocation rate because you cannot refill enough of these TLAB backs, what happens is that you should allocate out of TLABs. And according to the color scheme of Async profiler, Andrei chose, it could be confusing because in the CPU flame graph have a very different meaning. But in allocation flame graph, what you got is always the stack trace, and you have in Aqua the allocation within the new allocation in the TLAB. While in the orange one is when it's outside the TLAB. So basically the TLAB are not used and you allocate out of it. And in theory, it's not that simple, the story, but it's a good still summary of it. We care the more about the orange one allocation. And in the top, you have the type of object that is going to be allocated. Okay. So the orange one are the one you really know that could affect performance. The one are a bonus, but usually TLAB within allocation tends to be quite cheap.
Okay. In essence, my mental color scheme to remember this thing is aqua is good, other colors, let's see what happens, okay? Especially this orange one. Okay, so this is the ratio between on this thing. So when you do CPU sampling, aqua is good. The aqua, I mean this light blue, is good because it is the inline code. This is the fastest possible way to use a method without actually invoking it, but inlining it. So that's the good part. Here, the good part is the allocation inside TLAB, because this kind of allocation it's practically has no cost. The problem is, you see, this string builder is doing exactly the same thing. It's allocating an array of bytes. Okay. Sometimes when it is lucky, it allocates it inside the TLAB, which is okay-ish. It shouldn't, but let's say it's okay-ish. The biggest part of time is doing this. So it's the non-aqua part. It's the part of which we should be worrying about, or at least this is how my brain works with these kind of things. And yeah, what is surprising is that, again, with that fast fix, we wanted to limit the allocation. And now not only we are allocating a lot, we are allocating a lot in the wrong way out of the lab. Okay. As I said, Francesco spoiled the problem already. The problem is that, yeah, I am allocating a lot. I'm not supposing to allocate at each and every request, okay? What you normally do with a pool, you take a resource, you acquire a resource, use the verb that you want, but in essence, you acquire a resource and you use it, and when you are done with it, you put it back into the pool, which is something that our friend forgot to do here. So let's try to at least fix the problem and make the pool work properly. So as I said, we are doing this acquiring, but we are not doing this. Okay, and yeah, at least I'm using the pool in a proper way. Let's see if this improve the situation. Let's give this one more run. We
You have
want
to compile.
Thanks.
And in the meantime, events. So right now with CPU profiling, I told you what samples are, how they relate with the performance characteristic of the application. But in this case, it's slightly different because it's not at intervals. It's event-based. So when it happens, there is an emission of an event. That is very different because how you can tell that is too much or too few? You don't have a mechanism because you have no boundaries. You don't know how much. Actually, given that you have observed the orange part, you can tell that is too much. That's how you can spot that's too much.
Or anyway, that there is a problem there and you need to figure out if you can do something.
Yeah.
Sometimes you can't. But
And there is another interesting bit related to what you want to observe for real. Sometimes you are not interested into the fact that an event happened, but the magnitude of this event. But what's the magnitude of an allocation? It's the bytes allocated. So if you have a single event out of TLAB of 10 megabyte, you are not happy about it. But what happened is that you have a biased flame graph in this case, because maybe you have 1 million of samples of the good things and a very tiny invisible one of the out of TLAB. How to make it unbiased in this regard? You have the option in JFR to check the total bytes allocated. And that will show not the fact that you got an event, but that event, how much it costs, the out of TLAB. And it's accurate, actually.
okay.
And the same with the SIM profiler. So you got the total option to know
so
the magnitude.
in essence, what we are saying is that what you saw with the former flame graph is how many times you request an allocation out of TLAB or in the TLAB, but how many times you did. Okay, you are not seeing how big it is, which is probably even more relevant, right?
It could be.
Or could be, yes. So I don't remember the flag, Francesco, but if you want to see
For the total.
the total, yes. So
minus total.
Okay, this is the line where we launched the profiler. I'm not showing this now, but if you do minus total, I guess, right? If you do this, is the sides of the bar of the flame graph line will no longer be the number of sample, the number of allocation even, but the actual memory size of that allocation even. which is probably in some case more relevant.
Exactly, and it works slightly different between within TLab and out of TLab. Because as usual, the typical trade-off of profilers is to make it cheap, right? So you would like to observe carefully the things in which you are slow, and if you make it a little bit slow, is not a problem. But if you make the fast path slower, is not nice. We know that the fast path is the allocation within TLab. So for this reason, the profiler emits the event that you are allocating within a new TLab, but still within a TLab, only when the new TLab is created. So you can have plenty of allocation within it, but only at the end you have the emission of the event. So it's batching, it's amortizing the cost of emitting the event. With the out of TLab allocation is different because it's already slow. It's not super slow, but slow enough that you can be precise. And you can be precise enough that in the orange bar, if you check the bytes, is actually the right bytes, so allocated. That will make it even more relevant. That is what we want while we observe that event.
Okay, I'm pretty sure I compiled this, but we will see. Do you want to run this with the allocation event or just a plain one?
No, minus e alloc, it's...
Is it okay? Okay.
Yeah.
So let's give this a second chance. Again, just to recap, what I fixed here is that the pool wasn't properly used. It wasn't releasing the pooled resource after the use, so we should see a better result now, where we are actually reusing stuff from the pool, which is something that was not happening before.
And now we are going to get better number that's 3.
Yeah, yeah, okay, so this is the fast version, so we should get better number than before, yes. Let's see. Yeah, I believe. Okay, okay. Actually, it went fast.
It's quite fast.
Yes.
So much to name it fast.
Yes. Okay. Yes. So I don't remember what was my very first attempt with the non-fast version, but it was for sure above 100. Okay. I guess it was this one. And now I'm 110. Okay, so probably it's a little better. But probably it's within the error measure, right?
Yeah.
We, in this case, overcomplicated overcomplicated something that probably was already good enough. So probably it didn't worth the pain, and probably we were out of that 3% that I mentioned at the beginning of this talk.
Yeah, at the same time, given that now we have a tool to observe how things change, you know, in the real world, you won't get a single endpoint hammered, or maybe you got with microservices because the people like that. But beside that, the point is that you have a wider kind of operation in place altogether in a real system. And when it happens, it could be relevant to save some bandwidth and work to the GC just for the TLab thing, let's say. The point is that you should measure. And in the current, if we have a representative kind of test, this test is suggesting that is not worthy at this point. So if it is the type of service that we want to deliver. So that's very important to be honest from, you know, from a scientific point of view. It's not worthy and wasn't that fast actually. So.
Okay, I think we are done with this. Again, our example, well, probably. You want to? Sorry.
We got it. I mean,
the last one. Okay.
We supposedly have a cleanish one, so without the orange part.
Yeah. Sorry. Okay. Let's look for the name of our service.
Acquire, even too.
You want to see the acquire,
It is
okay.
the same.
I don't see it.
Good for us because we are
Yes.
pulling, so
Yes.
it makes sense.
So I should see at least I don't remember
The
the
to
name
string
of the
by the end.
method.
No?
This one. Let's see if I can find it, but probably I won't. Okay, easier.
Okay. That kind of makes sense because we perform a to string
okay.
by the end. No.
Okay, and now the allocation part, it's okay. It's a much smaller percentage. Now I'm focusing on the uh, rest endpoint method, but the percentage is much smaller, and you see the flame graph epicolor, the aqua color, so you know you are fine with this, right? In this allocation bit, I mean. Okay.
And additionally, last thing, as usual, during the whole talk, we take a look at what happened under the hood many times. And that's the other interesting part, the funny part, let's say, of profiling. In this case, what's funny is that it shouldn't be char array, a string. No, actually, because in JDK 11, probably, there was compact string that is making use of an optimization of a bit that determine if you have a late-in or not string. And because of that, you can use 1 char per byte. And you can spot here that the allocation is byte array, indeed.
It's not a char array.
So it means that even what you observe is a moving target is influenced by the runtime. It changes over time, exactly like your application, because it is a single experiment in a single point of time. So you should be aware and take note of it while performing any analysis. It doesn't work that you just do it for the last version of JDK, no?
Yes. It's a moving target.
It's a moving target.
Yes. Okay. So again, I think we are really done now. Probably our example was a bit simplistic. I don't know. Sorry if they were, but we wanted to demonstrate the workflow really. How we reason when we see a problem. Okay, the problem was in our example a bit probably artificial. It's made up, let's say. But yeah, and again, we wanted to show this not in isolation with a micro benchmark, but within all the also noise, let's say, that the usage of this stuff inside a framework or a stack of framework, as Quarkus does, can generate, right? So
there is something we can show. The folded one, because Mario,
the what?
The collapsed output.
Okay.
Instead of .html, you can do .folded. And I can explain why. It's related to what Mario is saying. Sometimes the overall framework looks like a noise. Even the fact that you can have stack traces of 10K, depth if you use the wrong framework, and less if you use Quarkus, for example. No, I'm joking. But the point is that sometimes it's disturbing to see so much data, no? The nice thing of this tool is that they allows to be manipulated, the data you got. And you can use, I'm using ChatGPT for that because I sucks in Python. And there is a format by which you can extract the profiling data called collapsed form. And you can use a script to collapse the stack traces. And in this way, if you have the hibernate thing, because you are using Quarkus, in that case, you have a single label saying hibernate, instead of having 10 method called, because we don't use that very deep stack. But the point is that it reduced dramatically the noise. So that's the other take of this workshop. These are tools. It's a knife. You can decide how to use it, and you can change it if you want. It's open source. I know I won't be happy, the author, but Depend, let's say. So
Yeah, I
if the
can
change
show
is good,
this.
yes.
I don't remember. I guess it's -f, right? -f
No, no,
collapse.
without -f. Just when you produce the -f, right, folded.
Folded this way,
Yeah,
right?
folded, exactly. You can use both folded or collapsed, and it's coming from the perf word. So it was the original text format that you can use with the sim profiler. And there are converters that allows to extract, again, the actual flame graph out of it after you manipulate them. But we will check. We have 7 minutes, but
Well,
can
yes.
take 1 minute actually. If
Maybe
you have
we-
any question,
Yeah, probably it
better.
will be nicer to leave some time to question if there is any. I know that this thing could be a little bit overwhelming, especially if you look at it for the very first time. Again, if you have a question or if you have feedback about this session, let us know even offline if you prefer. We are here. I will be here for the rest of. Yes.
Question, the IDE integrated profiler,
Okay.
actually the same?
is a sync profiler. At least
Yes.
IDEA is using a sync
Yes.
profiler under the hood. I don't know if it's using the same Java wrapper called the API loader. I have no idea, but it's what you got. The flame graph visualization instead is provided by IDEA itself, but the data are coming from there, definitely. And you can get, so
Yeah, I don't know.
it's nothing,
I
so
I
fancy.
believe
But
it won't be
to
really
show you
readable now. Yes.
what it is. So you got a single line, the first line. You can see in the left part you have the row number, the actual line number. A single line is just the base of the thread name in the upper left. So vertex event loop thread 0 with the thread ID. That's what you read in the flame graph, actually. The full name of all the ancestors that represent the stack trace. And right at the end, you have the weight of the sample. And it's done. It's nothing more, really. So you can take a couple of lines, paste it on ChatGPT, that's what I do, and I say, I would like to be able to find the ancestor, making the sum of them and using label to replace it.
Yeah. So
And-
the essence is that
And it doesn't work, actually, the first attempt, but he tried hard.
Some text manipulation. You can query this stuff. Is not. It's quite a readable format, but it's of course very very verbose. So you are not supposed to read it. You are supposed to parse it in some way if you want. Yes.
Yes, and then you can still use the other converter tool to
Yeah.
make it the actual frame graph. And it reduced a lot the noise in the real world, actually, when you have long stacks, unless you use the right now. I will stop. Okay.
Okay. I think this
that's
is all
really-
we have. Is there any more? Question.
So, as almost all of your time is now spent in kernel space, does it help to start for Quarkus looking at other implementations like IOU or something?
I have implemented IOU ring for Quarkus because I'm a netty committer. So we do have IOU ring already available for Quarkus, exactly for this reason. We didn't show this because it was already very generous to pitch Quarkus so much, but it's real. If you look at this syscall representation through CPU flame graph, it's a different thing. You have so much less orange, actually, as you expected. For the people that doesn't know, IOU ring is an asynchronous interface to talk with the kernel. So you would like to read, you ask for read, and it will happen. No, and that kind of thing saves a lot of CPU time, actually, when you are bottlenecked there. As usual, it's a trade-off.
More question? Okay, thanks a lot. Thanks for having us for 3 hours. We hope we didn't kill you, and we hope, of course, you enjoyed it. it and learn something. Yes. Thanks a lot. And yeah, if you want to play with our repository, feel free to clone this and feel free to ping us, send an email, or yeah, we will find a way to get in touch with us if you have any questions. Thanks.